In this series of practice, we're going to explore the density of a gas. So in our case, we have 100% dioxygen, and the pressure is 100 atmospheres. So deep sea base on the bottom of the ocean might overpressure in order to create enough outward force to hold back the weight of water trying to crush it. So if you were in such a facility on the bottom of the sea, this might be the pressure inside the submersible. Your breath is still going to be 1 liter. And for simplicity, we're going to use the standard freezing temperature. Take a minute, see if you can just solve the density of this gas. What is the density of pure oxygen at 100 atmospheres? All right, if you're back, well, remember that our density was equal to the pressure times the molecular mass divided by R divided by T. We could reorganize the ideal gas law to create a calculation for density. Well, I know my pressure, it's 100 atmospheres. It's dioxygen all the way through, so it is 32.00 grams per mole. R value in atmospheres 0.08206 and 273 Kelvin. Want to calculate that out? 143 grams per liter. That is a very high density. Most of the time, the air you breathe is about 1.2 grams per liter. So this is it's about 100 times, a little over 100 times more, which is just because our pressure went up. Think about the formula. If your pressure was 1, you'd multiply the top by 1. If your pressure was 20, your top would be 20 times larger. When our pressure is 100, the top is 100 times larger than 1 atmosphere. Increasing the pressure of the gas just means there's more gas around, so the weight of that gas goes up. Now, why this is a problem? Well, your lungs are built to push what you normally breathe. You normally breathe about 1.2-ish grams per liter. So your muscles are designed to move that kind of weight. If you suddenly had 100 times the weight, that's really difficult. You might be able to curl a 5-pound weight really easy, but can you curl a 500-pound weight? No, the 100 times is obscene. Even though 143 grams doesn't seem like a lot, your lungs aren't built for it. You literally would die from suffocation because you couldn't move the air out of your lungs. We do actually sometimes overpressure deep submersible devices in order to increase their resistance to the ocean pressure. And so scuba divers, things like this, they'll often have what's called heliox. This is a helium-oxygen mixture. We replace some of the oxygen molecules with heliums, which weigh significantly less. And so in this case, let's look at a mixture that is 80% helium, 20% O2 by moles. If 80% of the moles are helium, that means 80% of the pressure is helium. Remember that your pressure of a gas is equal to the pressure total times the mole fraction of that gas. If 80% of our gas is helium, well, 100 atmospheres for total pressure, decimal form 0.8 for the mole fraction of helium is going to give us 80 atmospheres of helium and 20 atmospheres of O2. So inside this deep diving scuba tank, this is the actual mixture. Take a minute, use this data, see if you can calculate out the density of air with this mixture. All right, if you're back, well, how do we solve it? Well, the idea is the gas is a mix. Some of it is oxygen, which will have some weight. Some of it is helium, which will have some weight. If we can determine what each of those are, the total is just the sum of the two. Same way our pressure is the sum of the pressures, the weight is the sum of the weight. And the density is the sum of the densities. I can solve the density for my helium inside that 1 liter breath, and I can also solve the density of the O2 in that same breath. They're taking up the same space. You've got your lungs. There's some gas in here. There's a little bit of another gas. Well, if you just look at one of those, you could say what's its weight in that volume. And then you could look at the other one and say what's its weight in that volume. They simply are the sum of the two weights in the same volume. And so I could solve the pressure for the helium as 80 atmospheres. Molecular mass is 4 gram mole. 0.08206, 273. For the dioxygen, it's 20 atmospheres. 32 grams per mole. 0.08206, 273 Kelvin. This will give us a density of 14.23 grams per liter for our helium. And for our dioxygen, 28.6 grams per liter. Our density total is going to be the sum of the two, 42.87 grams per liter. Now, this 80-20 mix certainly still weighs far more than a normal breath on the surface, but it is significantly more reasonable than the 143 grams of pure oxygen. By cutting the mixture with helium, we have actually reduced the density, so your lungs don't have to work as hard to move the gas mixture. If anybody ever saw the old movie Sphere, Michael Crichton book, don't recommend it. But there was this funny bit where they're talking in really high-pitched voices because the facility they were in is filled with helium so that people can breathe. Deep-sea divers who go down a couple hundred meters, so deep oil well rig welders. And yes, there is a job that involves welding underwater several hundred meters deep. You have to have special training on how to breathe at that depth. And the mixtures of gases are there designed to help reduce the weight so that you can breathe more easily. In fact, those mixtures go even more extreme. Normal oxygen might be 20% on the surface, but there's so little pressure that that's not a significant amount of gas. If you're at a much higher pressure, you need less percentage of oxygen to have the same amount of oxygen around. So finding a 90-10 or even a 95-5 helium to O2 mixture is possible, and you can still survive on it. Well, we might need 20% dioxygen at the surface at 1 atmosphere. Well, if you're at 5 times the pressure, that would mean there was 5 times the oxygen around. So you could have 1/5 as much around and end up having the same amount of dioxygen. And so we can cut our percentages much lower and still have enough oxygen to survive.